The next talk has the topic OpenCL for heterogeneous computing on embedded controllers. And I'm glad to welcome for this talk the speaker Prakash Balasubramanian. He is a software architect for heterogeneous computing at Infineon. I wish you an interesting talk.
Welcome to this webinar on parallel computing. I am Prakash from the automotive division of Infineon Technologies. I'm here to share with you my experiences on heterogeneous computing frameworks on microcontrollers. My main aim is to demonstrate that some of the heterogeneous computational frameworks associated with the x86 systems typically are equally applicable to microcontrollers as well. The presentation is organized as following. We will quickly refresh our knowledge of computer organization of multi-core computers. We will then spend some time on learning parallel computing on homogeneous systems. We will thereafter make the move to heterogeneous systems and understand how parallel computing is accomplished on such systems. Having done that, we will apply the heterogeneous computing concepts on homogeneous multicores and recognize the flexibility such an adoption brings to application development. So let us start without any further ado. You will find on the slide two computer organizations. On the left is a computer comprising CPUs belonging to the same instruction set architecture, all of them annotated as ISAX. Each CPU has a local memory. It may or may not have access to local memories of other CPUs. There can be a shared memory element necessary for software running on the CPUs to synchronize amongst themselves. So that was the homogeneous topology for you. On the right side, we find that the computer has CPUs belonging to different instruction set architectures, such as ISA X, Y, and Z. And when you see something like this, you wouldn't be wrong in calling it a heterogeneous computer. The term parallelism means different things to different people. Let's try to organize the various views. The hardware view of the parallelism is presented on the right. Nearly every computer has these attributes, nearly every modern computer. When multiple instructions are capable of being executed in parallel, such a computer is supposed or it is said to have the property of ILP, which expands to instruction level parallelism. When an instruction results in the same exact operation performed on a lot of data at the same exact time, the machine is demonstrating the property of data level parallelism, abbreviated as DLP. An ILP computer may or may not be necessarily DLP, but the converse is not true. It is extremely rare to find a DLP machine which is not ILP. It is like watching through your telescope a cow jumping on the moon. The software folks have a slightly different notion of parallelism. Their main quest is in trying to get as many independent software functional blocks execute concurrently. This gives rise to several programming paradigms. SMP, which expands to symmetric multiprocessing, it is typically applicable to homogeneous cluster of CPUs. The operating system schedules independent tasks on multiple CPUs as the case may be. BMP is similar to SMP. While pretty much any task can execute on any available CPU, some tasks will only execute on some CPU. AMP is a paradigm in which different applications execute on different CPUs. Please bear in mind that AMP applies to both homogeneous and heterogeneous topologies. But the parallelism that we are really interested in talking about today belongs to a class of programs called single program multiple data, abbreviated as SPMD. So these are essentially copies of the same exact task but operating on different data. Let's now look at parallelism, which is typical of homogeneous partitions. To start with, there is this coarse-grained task-level parallelism, typically accomplished by means of an operating system. It may so be the case that the business logic of a task pertains to performing similar computations on multiple data elements. For example, there may be the case that one of the tasks which was scheduled by the operating system, may be required to scale many elements of a vector by a constant. In such a case, the data may be split into partitions, and the scaling operation on each partition may be performed on a different CPU. This is typically accomplished by a paradigm called thread fork join model. Two industry adopted frameworks for TFJ, thread fork join model exist. The OpenMP and the Unified Parallel C. The UPC is based on the PGAS model, partition global addressable memory, and the OpenMP is based on the shared memory model. Just to make things a little clearer, the picture at the bottom, the one that has the mouse hovering on, it starts off as a single thread. So this could be the master thread of a task that was scheduled by the operating system. And then at some stage, there is a possibility that an operation is required to be performed on multiple data elements. So this results in several fragments of that code forked on multiple CPUs. Well, forking is not enough. You must also execute it. So not only are the threads forked, but they are also executed on multiple CPUs. Each fork produces a result. They are then amalgamated, and then the control returns back to the master thread or the single thread. And then the story continues. Let's take a look at both OpenMP and UPC. So apologies for the micro-sized fonts. In the case of OpenMP, the main programming language is essentially C. It could also be C++. However, the users write, or let's say the users annotate several parts of code which they think is parallelizable and can be parallelizable. The compiler then inserts calls to runtime, which then clones the parallelizable regions onto a certain number of CPUs. In the case of UPC, there is no dynamic forking of parallelizable regions. The complete task is run as SPMD programs on multiple CPUs. and each one knows what data are they to operate on thanks to their identity. So that was everything about parallelization on homogeneous partitions. Let's turn our attention now to SPMD on heterogeneous partitions. Now, this is important. The case that we are specifically concerned about in this discussion is that of the master core worker core topology. The master cores can be general purpose processors like the RISC processors, whilst the worker cores can be specialized processors like a DSP or a modem processor or a imaging processor. Often the master is in charge of complete application lifecycle management of the worker core. This could mean having to load the programs onto the worker cores and at some point in time requesting for remote procedure call services. The middleware infrastructure is typically custom and vendor specific. But should the worker core turn out to be a GPU or a GPGPU, then it's a completely different ball game. The de facto framework or the de facto standard for this middleware is generally CUDA for NVIDIA GPUs or NVIDIA devices, if you will, and OpenCL for everything else, including the NVIDIA devices. Now, before we get into the discussion on OpenCL, let's try to understand how SPMD programs are executed on GPGPUs. So the GPGPUs are organized into these gray colored boxes. These are known as the compute units, also known as streaming multiprocessors. Each of these streaming multiprocessors has what is known as a streaming processor, many of them. On my AMD notebook, the Vega GPU has 6 compute units, and each of them has 64 streaming processors. So it's 384 in all. Now, it is on each of these streaming processors that an instance of the SPMD program is running. You may have come across a term called SIMT, SIMT, which expands to single instruction multiple thread. Essentially, what they are saying is that at any given point in time, these streaming processors are executing the same exact instruction of the SPMD program. If that was theory, then let's try to understand how a real world computation happens on the hardware that we just learned. So here's a picture of here's a famous picture. Let's just state it. This image is partitioned into 3 segments, and each segment is then handed over to a compute unit. The streaming processors of each compute unit are then entrusted with the responsibility of crunching pixels belonging to that partition. So, in other words, or in plain English, this is essentially division of the same exact labor amongst the various compute units. So, a lot of streaming processors and compute units have collaborated. In the end, they have executed the same exact program but on various partitions and various pixels. So that was SPMD for you in action on a GPGPU. OpenCL expands to Open Compute Language. It was originally invented by Apple. It is now owned and sustained by the Kronos Group. Don't let the expansion fool you. OpenCL is not merely a programming language, but also a framework for um, addressing many aspects of the programming model. So let's see what are they good for. Uh, let's start with this wavy depiction. So this wavy depiction is essentially a software thread. It is essentially an instance of the SPMD program. The language aspect of OpenCL lets you write these threads. The OpenCL execution model helps define how these programs may be run. To be specific, on how many compute units should these programs be run and how many processing elements of each compute unit may be utilized or exercised. The OpenCL model defines a memory hierarchy. You will find private memories which are private to processing elements. And then for each of the compute units, there is this local memory. No processing element may access the private memory of another processing element. But if there is a need for them to synchronize, then data is returned to the local memory, and then another processing element then retrieves it from the local memory. And if the synchronization must be done amongst the various compute units, data is then returned into the global memory and retrieved by the processing elements of the other compute units. So that was both intra-compute unit synchronization and inter-compute unit synchronization. The OpenCL platform model, gives or offers a standard set of APIs to communicate, to allow the software running on the host processor to communicate with the software threads running on the device. The communication between the host processor and the device is by means of a command queue. The host processor gets memory management and execution of SPMD programs done via these command queues. And these command queues are basically the cornerstone of the discussions which is about to ensue. What you will see on this slide and what is depicted on this slide is a typical software organization of the computing stack. On the host side, of course, there is the application which is built on top of what is known as a host runtime, an OpenCL host runtime. This OpenCL host runtime, in all fairness, are the eyes and ears of the application. Everything that your host application needs to know about the device and everything that it needs to execute something on this device is accomplished with the help of the interfaces provided by the runtime. Now, the nature of the runtime plugin is entirely dependent on the device itself. So if you have more devices, you should expect more plugins. each one of them corresponding to the device that has been incorporated into your microcontroller or SoC. So here we go. So, here's a picture depicting multiple devices. Not only is there a GPU integrated, but there is also a C++ device like a SIMD processor, and then there can also be many scalar processors, essentially forming some sort of a RISC farm. Now, note carefully that for each of these devices, there are these dedicated queues, and each queue is managed by a device plugin. And the nature of the plugin, as stated earlier, is a function of the device for which it was written. For example, in the case of GPU, the device plugin may be in charge of not only loading the complete program into the memories of the GPU, but it may also have to press the start button. It could basically be turning on some bit into a programmable register, thereby starting off the grid operations. In the case of scalar processors or vector processors, there may be a robust middleware stack, and then all that the plugin has to do is pass on a telegram or a message to the middleware stack on the other side saying, hey, please execute this function for me with these parameters. So, long story short, multiple devices, multiple plugins, and each one of them is written or implemented differently based on the underlying nature of the accelerator. Okay. Now that we know OpenCL framework pretty much applies to the world of non-GPUs, let's try putting it to good use on microcontrollers. This picture is that of a fictitious microcontroller. And this microcontroller has CPUs belonging to three instruction set architectures, X, Y, and Z. And we have created a compute farm out of these spare CPUs or out of these devices. Now, OpenCL will let you create these devices, not just complete clusters of homogeneous CPUs, but you could also end up breaking this cluster into smaller clusters. Yeah. For example, this cluster of 4 CPUs can be broken down into smaller clusters of 2 CPUs, 1 CPU. I mean, you don't see the picture on this slide. A small cluster of 3 CPUs, and then, of course, the complete cluster of 4 CPUs. The point to note here is if you had a cluster of or let's say you submitted jobs to multiple clusters, they can of course be accessed in parallel. The point that you must bear in mind is that the sum of the CPUs allocated to the smaller clusters that are exercised may not exceed the total number of physical CPUs. And also, no CPU, by the way, has any affinity to any cluster, so they are sort of mercenaries. So this opens up many interesting options. For example, you may submit a job to a cluster made up of the complete set of spare CPUs, or you may break down these homogeneous CPUs into two or three clusters and then submit independent jobs concurrently. You could also submit a job to the homogeneous partition, and at the same time, you may submit a job um, to a device or a partition which is of a different ISA, as long as there are no data dependencies between the two clusters, or you could do something as crazy as this. So sky's the limit, your imagination is the limit, but in the end, you will be constrained by the nature of your application. So there are some APIs provided by the runtime. The runtime makes the job of the programmer that much simpler. Notice how these APIs may be exercised to obtain the properties of many devices on the machine. So you could use this API to find out how many devices exist on your platform, what are their characteristics, how many jobs can they accept, things like those. So, and in the end, if you will carefully notice these ND range kernel APIs, you will notice that essentially the application is submitting its jobs to various queues. So each queue is meant for a dedicated accelerator, and therefore it's apparent that multiple jobs can be submitted at the same exact time. Yeah. Let's put this theory into practice. What you see on this screen is a textbook Kalman filter taken from Wikipedia. The uppercase letters represent, by the way, the Kalman filter is used for making state predictions in the wake of noisy measurements. So the uppercase alphabets represent matrices, and the lowercase alphabets represent vectors. So when you see something like fx, it simply means this is a matrix vector operation. This is a matrix multiplication operation. There is the matrix transpose, matrix inverse, vector addition, matrix addition, so on and so forth. So this algorithm was parallelized on the TC39 multi-core microcontroller on a tri-core board, on a tri-board. And many variations. There were many variations. In the first variation, the complete algorithm had its execution spread over 3 CPUs, with the exception of matrix inversion, which was performed on the master core. And the speed up was in the range of 2. What is the speed up is in relation to this complete algorithm running entirely on one CPU, CPU 0, with all of the data in its local memory. So the ratio of the cycle count was taken, and it turns out that for both 24 states and a 48 state Kalman, the speed up is in the range of 2. In the next variation, we managed to sneak in some of the computational steps onto the master core. So both the farm comprising the 3 CPUs and the master core, they were awfully busy most of the time. And it turns out that the 1.96 and the 2.16 have marginally improved to 2.08 and 2.2. And in the next variation, we threw in a couple of additional CPUs into the mix, and the speed up for the 48 state Kalman increased to 2.4. And here's a nice chart depicting the increase in speed up as we increase the number of CPUs, but this should not come as a surprise. Um, yeah. Okay. On this slide, you will notice that not only are the jobs getting uh, spread over homogeneous partitions, but there is also a possibility to submit the job to a radically different processor, such as a SIMD processor. For example, the eigenvalue decomposition is a heavy number cruncher, so it requires a lot of cycles. So assuming that the eigenvalue decomposition has no data dependency on any of these computational steps, then the application running on the CPU 0 may also submit a job independently to the SIMD processor. So the third generation of Oryx, known as TC3X, not only incorporates the Tricore 1.8 CPUs, but it also incorporates a SIMD processor. And this is something we have already experimented with some excellent results. So we have now come to the end of this presentation. Some key takeaways. OpenCL is not meant merely for CPU GPU topologies. It is absolutely relevant and applicable for the non-GPU type of accelerators as well. You can deploy the OpenCL framework on homogeneous multicores whose programming language is not OpenCL, but it could be C or C++. C, by the way, is my favorite. You can not only exercise the homogeneous partitions, but you may also be able to exercise the heterogeneous partition at the same exact time, thereby maximizing the usage of the available compute units on the chip. It's fair to say that the nature of programs which will benefit the most from this framework is the SPMD single program multiple data styled program. As and when you continue to add new compute units to your microcontrollers or SoCs, you will find that revectoring or retargeting some of the computations to the newer compute units requires extremely small or minor changes in your main application, because all that you have to do is change the command Q, and then that's it. And then the middleware on your new device takes care of the execution. We have reached the end of this presentation and will open the floor for question and answers. I will be happy to clarify any questions that you might have. So thank you very much and talk to you soon.